Hi everyone. Today we're testing one of MikroE's RTK clickboards, a tiny evaluation board that's about the size of an ESP32 but packed with advanced features. We'll connect it to a tablet and show you how you can get centimeter level accuracy in real time using Swift Navigation Skylark corrections. Let's jump right into it. MikroE makes a wide range of RTK clickboards, built around receivers from leading brands such as Quictel, Septentrio, Unicore, u-blox, all compatible with Skylark. This one here is the original GNSS RTK click, featuring the popular u-blox ZF9P receiver. You'll notice pins for UART, I2C, SPI, plus status outputs that indicate when the receiver is ready or in RTK fixed mode. There's also another set of serial pins for the module to receive an RTCM correction stream. Up top, it has an SMA connector for the GNSS antenna. This board uses the F905B, a dual-band L1-L2 receiver, so we'll connect it to an L1-L2 antenna for full dual frequency operation. And here's the micro USB connector, which is perfect for both power and data. We'll grab a micro USB to USB-C cable and plug it into our Android tablet. Okay, next we'll stream RTK corrections to the board using a handy Android app called GNSS Master. We open the app, go to GNSS receiver connection, and make sure USB serial is selected. You'll see the u-blox receiver appear, and we tap connect. Next, we tap on correction input and enter our Ntrip credentials, which can be found at account.swiftnav.com. This includes the Ntrip address and port. For the mount point, we select NXRTK MSM5, have our username and password, and make sure that send NMEA GGA is checked. That's required for VRS operation. We tap save and connect, and you'll see a confirmation that we're receiving corrections. And the RTK status LED on the board starts blinking, which is a good sign that RTCM messages are coming in. Now we want the tablet to use this receiver's position instead of its internal GPS. And to do that, we'll enable something on Android called mock locations. The app reminds us that we first need to grant this permission under developer options. Now, on most Android tablets, you enable developer options by going to Settings, About, and then tapping the build number 7 times. Now that we are a developer, we can go back to System, Developer Options, and scroll all the way down, tap Select Mock Location App, and select GNSS Master. And we return to that GNSS Master app, and now we can turn on mock location, and it works. Any app that uses location now benefits from our RTK corrections, but it's still hard to see the difference unless we have a way to visualize it. So at Swift, we've built a simple demo app called Swift Map Demo to help visualize GNSS accuracy in real time. Let's open the app. Out of the gate, since we're using mock locations, this app, like all other running apps, is using the RTK receiver's position. And we could start plotting our track, overlaid on a satellite image, and observe how precise our position now is. But that reported accuracy of 80 centimeters seems off. That's because out of the box, the F9 doesn't output the GST NMEA message, which includes the standard deviation of latitude and longitude errors, which are needed to compute an estimated accuracy. So we'll want to enable these GST messages using the u-blox uCenter tool on the computer. To do that, we go to the Generation 9 configuration view, Advanced Configuration, and search for GST. Message out is what we're looking for, and we'll find the GST USB parameter nested in, which is currently set to 0. We change its value to 1 and save it in memory and send the changes to the F9. And we can check that the bit changed indeed to a 1. Back to our Swift Map Demo app, we immediately see the accuracy field update in real time, and it's now showing about 5 centimeters. We could stop here, but Android Android's Mach location system doesn't pass through the RTK fixed type, so let's go one step further. Back in the GNSS master app, we'll enable a server that outputs the full NMEA stream over TCP/IP. We go to receiver data output, mode, we choose TCP server and a port, say 55556, and tap connect. We can now turn Mach location off because we won't need it anymore. Then back to the SwiftMap demo app, we tap on source and change it from Android's fused location provider to NMEA source. We'll use the tablet's own IP address, which is the default value, and set the port to what we chose, and give it a name, say Skylark. And we hit OK. Now the app is ingesting the raw NMEA stream directly from the RTK receiver and can display the actual fixed type, in this case RTK float. And we still get the estimated accuracy from that GST stream we enabled, which now shows 2.5 centimeters. Another cool thing we can do now that we're not using Mach locations is run two instances of the app, one using the RTK receiver as the location provider, and another using the tablet's internal GPS receiver. Let's open a second instance of the app by tapping on the app again from the home screen. Now, because Mach location is off and the source is set as Android's fused location, this instance is simply using the tablet's own receiver. Let's name the stream uncorrected, and we'll change its track color to red. Now, to get the two instances running side by side, tap the square button, choose Split, and select the first instance. We now have our RTK receiver on the left in RTK mode, and the tablet's own GPS on the right, uncorrected and in SPP mode. Let's take them out for a quick drive. So we have the tablet mounted on the windshield and the clipboard and antenna firmly set on the dash right next to the tablet. Now on the apps, we can set the follow mode and turn the live camera overlay. When replaying the recording, it will show us exactly where we were, therefore acting as a source of truth. We can hit start to draw our tracks, and let's go. As we drive along, we can see how the Skylark side in blue is spot on, showing us on the correct lane in its center, while the uncorrected side in red isn't even on the road itself. That's why in standard navigation apps, the blue dot is pinned to the center of the road, if you've noticed. Without GNSS corrections, it's actually impossible for your phone's GPS to know which lane you're on. Case in point here, we just changed lanes and only the Skylark side was able to accurately follow. At the end of the drive, we can overlay both tracks on the same map by importing their log files. Again, blue for Skylark and red for uncorrected. And we can retrace all our drive. And of course, you can do the same to compare different clipboards against each other or even test multiple Skylark variants, for example NX-RTK versus CX, in order to decide which best fits your application. Whether you're testing GNSS modules, evaluating corrections options, or just exploring what centimeter level precision can unlock, this little clipboard paired with Skylark is a great way to start. Thanks for watching and happy navigating.